Morning, sir.
Good morning. So is the slides visible?
Yes, sir.
Okay, all right. So let us summarize what we have done in the last class. In the last class, we started looking at the heat transfer from the extended surfaces, isn't it? That's what we have started looking at. We said that the heat transfer from the extended surfaces is extremely important in the practical application, primarily because very often we need to dissipate the heat in the ambient, isn't it? And the heat dissipation to the ambience will be primarily by convection. And since the medium is air, there is little we can do in terms of improving the convective heat transfer, isn't it? Unless we create a turbulence, but it's not economical all the time to create a turbulence in the ambience, isn't it? For instance, if you are having a engine, then every time you will not be able to create a turbulence around the engine, isn't it? Because this your vehicle is moving all the time, isn't it? So that choice is not available. So the other options are either we can improve the heat transfer coefficient, or either we can improve the heat transfer area, isn't it? So the extended surfaces primarily does the same. They improve they increase the heat transfer area, and because of that the convective heat transfer to the ambience or gaseous medium is improved because of that. Okay, so then we have looked at two cases. First was the complex generalized case, where we have kept the assumption that at x equals to L, the heat transfer from the leading edge will be given by Newton's law of cooling. That's what we have assumed. So that is the this particular case is the generalized case. Okay, so with this we have obtained the expression for how the temperature will be distributed along the longitudinal direction, isn't it? Also, how much heat will be dissipated from the fin, that also we have obtained the expression. Then usually the fin efficiency is calculated as the actual rate of heat transfer divided by maximum rate of heat transfer, assuming the uniform temperature TW. Okay, so this is the theoretical maximum. You will not get this maximum at all. This is a theoretical value. Why we are saying the theoretical value? Because the temperature of the fin is maintained at TW throughout the longitudinal direction. That is not possible. Okay, so with this theoretical calculation, the maximum rate of heat transfer we have calculated, and that we have divided to this maximum rate of heat transfer, and that gives the efficiency of the fin, and the expression for the efficiency of the fin is obtained like this. Okay. Again, you can see that the efficiency of the fin, it does not depend on the temperature, isn't it? You can see there's no temperature term here. Okay. Then we have looked at the second case. In the second case, what we said that usually one should design the fin such that the entire temperature difference should be exhausted by the time you reach to the end of the fin, isn't it? That means there is no temperature difference between the ambient and the temperature of the fin at the end of the fin. That's what usually we consider when we are designing the fin. So we will increase the length of the fin to that extent where my temperature at the end of the fin becomes the same as the ambient temperature. So with this condition, my boundary condition changes to at x equals to L, heat flux becomes 0. Okay, so with this boundary condition, then we get much more simplified expression as so the temperature distribution is given by T minus T naught divided by TW minus T naught is equals to cos hyperbolic zeta L minus x divided by cos hyperbolic zeta L. Okay, similarly, we have obtained the expression for the fin efficiency. Then we have extended our discussion on finding the critical insulation thickness. So this critical insulation thickness is very important, because in a process application, very often in order to minimize the heat dissipation to the ambient, what we do is we apply a insulation over the metal surface A typical example is a pipe in a hot fluid. Usually we wrap that pipe by using a insulation so that the heat dissipation is avoided to the ambience. Okay. Now in such cases what happens is more the insulation you add, the radius, outside radius of the pipe increases, and because of that the convection increases. Even though the conduction is decreasing because of addition of the insulation, but convection increases because outer surface area is increasing. So there is a maxima present. If you increase the insulation thickness from the bare pipe, you will see that initially the rate of heat transfer increases because of the heat transfer area is increasing, but then it starts decreasing. So there exists a maxima at which the heat loss to the ambience is maximum. Okay, even though we are applying the insulation, and therefore the insulation need to be maintained higher than this critical value. So this particular limit is called as a critical insulation thickness, isn't it? So this is what we have, discussed in the last class, and we have also obtained the expression for the critical insulation thickness when we are putting the insulation over the cylindrical pipe, and that comes out to be this critical radius of the outer radius comes out to be K by H naught, whereas critical insulation thickness is K by H naught minus Ri. Yes, is there any question, Achintya? Anybody? Hello? Somebody said something in between. All right, if there is no question, the last part which we have looked in the last class was to obtain the economic insulation thickness. So we said that if we put the insulation, what we are going to get? We are going to get the saving. Okay, so there will be heat loss from the pipe is going to take place, isn't it? So that is the operational cost in a way, isn't it? And also if you are putting the insulation, then that will also going to cost you some money, isn't it? So in a way you wanted to find out the optimum value of the insulation thickness at which both this operating cost as well as this insulation cost becomes minimum. Okay, so that's what we have calculated here. So economic insulation thickness basically minimizes both. So basically we are minimizing the both these cost factors, and what we are going to get here is the economic insulation thickness. You will see that. So P1 here is the cost because of the loss of the energy, isn't it? Loss of the energy. So that decreases as your insulation thickness increases, whereas as your insulation thickness increases, your cost for purchasing the insulation increases. So there exists a minimum point which accounts both these factors, and that particular point is called as the economic insulation thickness. So up to this we have seen in the last class. Is there any question so far? Hello? Hello? Is there any question so far?
No, sir.
Okay. Okay, so let us look at one example. So this is a similar. This is the same example which we have extended from the heat conduction. Remember, in the heat conduction we were looking at what type of expression we are expected to get when there is a current flowing through a wire, and then there is a resistance, there is a insulation applied over the pipe, over the wire. So that case we have solved earlier in the conduction, but the only difference with that case and this case is, in that case you can see the boundary condition here we have used as at R equals to R naught, my TC is T naught. That is not a realistic assumption. Remember, in that case we have assumed that this T naught is just the skin temperature outside here at the surface, isn't it? That's what we have assumed in earlier case, correct? But that is not the realistic assumption. So very often the skin temperature is not known because that can vary also, isn't it? isn't it? So very often people measure the ambient temperature or inside temperature here. All other surface temperatures are not easy to, obtain. Some variation you may get there, isn't it? So, and also see, so more realistic assumption in this case would be what? At R equals to R naught, my heat flux should be same as heat loss by the convection, isn't it? Do you agree or not? Okay, I will show that case. Maybe then you will appreciate what I'm trying to say. Okay, let me just go back to the conduction slides. Just a minute. Okay, so remember, this is what the example which we have seen. Just a minute. Okay, this is the example which we have seen, isn't it, in the conduction. So in this particular example, what assumption we have used in the boundary condition? See here, at R equals to R naught, we have used TC equals to T naught, which is not accurate. So here T naught is just this skin temperature. So we are assuming that the ambient temperature and the skin temperature is same here at the outer surface, but that's not going to be true in a real operation, isn't it? In a real operation here, basically my heat flux will be same as the heat dissipated to the ambient by convection. Do you agree with me or not? Hello?
Yes, sir.
So in this case, in the conduction, we have used this simplified case because at that time we have not studied the convection at all. That's why we have assumed that the skin temperature here is same as the ambient temperature T naught. But in a real case, we will have a thin air film outside here that will have some resistance, and because of that the skin temperature here will be different compared to the ambient temperature, and the skin temperature will be unknown, and therefore the boundary condition at R equals to R naught should be my heat flux at QR at R equals to R naught should be equals to H delta T, and H will be the outside heat transfer coefficient, delta T will be the skin temperature Tc minus T naught. Do you all agree?
Yes, sir.
Okay, so this particular case we are solving in the example which I am presenting. Okay, so let me again go back to our original. So is it visible? So see here we are saying that so these are the same expression. These are the same expression I have borrowed from that example from the conduction, isn't it? So I have not derived this again. So remember the temperature distribution in the metal wire will be given as Tm, and that will be given as minus R square psi V divided by 4 km, where psi V is the volumetric rate of heat generation and C2 is the integration constant. Of course, C1 will be the integration constant. One more integration constant will be there, but that we have found that it is 0 because dTm by dr at the center will be 0, isn't it? So C1 becomes 0 automatically there. Do you all able to recall what we are saying?
Yes, sir.
And similarly, TC is also, we have obtained the expression for TC there. So we are starting from these two expressions directly. So TC is C3 ln R plus C4. Now in these two expressions, here you can see that there is a volumetric rate of heat generation only in the wire. There is no volumetric rate of heat generation taking place in the insulation, which is outside the wire here. Okay, so for the temperature distribution in a insulation, the expression which we have obtained is Tc is given as C3 ln R plus C4. So these are the two expressions which we have obtained earlier. So is it clear to everyone, these expressions? These are the same expressions which we have derived earlier in the conduction slides. Is it clear?
Yes, sir.
Okay, so now again let's apply the boundary conditions here. So what is the what will be the boundary condition here? So we are saying that at the boundary of this metal wire and this insulation somewhere here at R equals to Ri, my temperature Tm will be equals to Tc. Also, the heat flux is going to be the same, isn't it? So Tm will be equals to Tc, and also minus Km dTm by dr should be equals to minus Kc dTc by dr. So I am equating the heat fluxes at R equals to Ri. Is it clear?
So why Tm equals Tc?
Because
Why?
both the temperatures are going to be same here at the boundary here, isn't it? Because both metal and the insulation are connected, isn't it? So at the boundary, what will be the temperature?
But sir, Tc is the temperature of the outer surface of the insulation, right?
No, 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 no. We are
If
saying that Tc is the distribution of the temperature across this insulation. Across this insulation.
So we are assuming it to be uniform throughout.
No, no, no. We are not assuming uniform. It is going to change. That's why it is varying with respect to R. You can see equation 2.
Oh, okay.
It is varying with R. It's not same.
Sir, we can only take Tc equal to Tm.
Remember in the previous case.
So we can only take Tc equal to Tm at steady state. Like at any other state.
This example which we are looking at is a steady state example, isn't it? We are not saying any, this expression we are not getting any differential equation in terms of, remember this equation we have derived where we assume that there is no accumulation term.
Yes, sir.
Isn't it? So that means it's a steady state thing we are looking at. Is it clear or not clear still?
So clear, sir. But at non-steady state, can we equate heat transfer? Because we won't be able to equate this temperature.
So in unsteady state, we will get slightly different equations. Okay. But at the boundary still you can say continuity has to be there. Na? Remember this Tm equals to Tc that we are taking at the boundary here because that's a continuity, isn't it?
So continuity should be in the heat transfer, not in the temperature. Like heat transfer continuity is more important than temperature.
So okay. So I give another thing. Okay. So if you so what we are saying here is at this boundary, what should be the temperature? Do you think there will be any do you think there will be any sudden jump or sudden drop in temperature? That is what your question is, isn't it?
Yes, sir. At unsteady state, there might be.
No. I'm at unsteady state also. I am saying that will not be there. See, in a steady state, you get a kind of a straight line. Here you will get a straight line as a increase or decrease in the temperature. But in an unsteady state, you might get a curved line. You might get a curved line, but you will not have a okay. So what I'm trying to say here is, so for instance, let's say if we are having let's say I am having 3 blocks. Okay, this is what I have shown earlier also, if you remember. So how my temperature is going to be in this case, in such cases? My temperature, where I am having a steady state, my temperatures are something like this. Up to this, there will be a straight line. Then I will have some different slope. Here I might have a different slope, something like this, isn't it? Yes or no? In a steady state.
Yes, sir.
But let's say if I am having an unsteady state, I will have something like this, a curved line up to this. Then there will be another curved line with a different type, isn't it? There will be another curved line here, but you will still have a continuity here. So both the temperatures will be same here. They are not going to follow the same nature of the curve after this point, but at this point the temperature is going to be the same. Do you agree or not?
Yes, sir.
That's what I'm trying to say.
Okay.
Isn't it? I will not have any drop like this. So if I go here, then this temperature drops here and then starts here. No, we will not have like that. Does it make sense?
Yes, sir.
Is it visible? Still my slides are visible to everyone?
Yes, sir.
Okay. So now, okay, so Tm equals to Tc and minus and flux Qx will be equals to Qm will be equals to Qc here at R equals to Ri. So that will be the boundary condition at inner point here, inner interface point here. What will be the boundary condition at this outer interface, which is the interface between the insulation and the ambient? So there we will have at R equals to R naught minus Kc dTc by dr. So this is nothing but the heat flux through this insulation at R equals to R naught. That should be equals to H Tc minus T naught. Isn't it? Where in this case Tc will be this surface temperature. So don't get confused with this. Okay, so here again this entire expression will be at R equals to R naught. Do you all agree?
Yes.
Sir.
Yes, sir.
Does it make sense? So this is the only difference we are having with respect to the previous case. In the previous case, what we have assumed as at R equals to R naught, we have taken Tc is equals to T naught. That's what we have taken earlier in the heat conduction slides. But here we are assuming the more realistic assumption. A more realistic assumption in this case is going to be at this outside boundary here. My heat flux should be whatever the heat is getting dissipated to the ambient. All right. Hello. So then it becomes easy. Then we can just solve this, isn't it? So put all these expressions. So this is just what? This is nothing but Tm I am equating to Tc at R equals to Ri. So R is changed to Ri. So with this I got this equation number 5. The second expression is minus Km dTm by dr should be equals to minus Kc dTc by dr. So that we have equated here. So by equating that we have got this C3 directly, isn't it? So C3 comes out to be Ri square psi v by 2 Kc. Again at R equals to R naught minus Kc C3 by R, isn't it? So that this C. These are the expression for Tm and Tc. So we can get dTm by dr just by differentiating this with respect to R. Similarly, dTc by dr we can get directly by differentiating equation number 2. So that's what we have done here. So Tc I have differentiated with respect to R. I got dTc by dr and Kc dTc by dr at R equals to R naught. That comes out to be this minus Kc C3 by R, and that should be equals to H Tc minus T naught at R equals to R naught. We can rearrange this. So in this expression, this Tc again we can put it as the expression given for this, isn't it? This is the Tc. So we can put it in this. So in this expression only unknown is C4. So C4 we can again find out because C3 we already know from equation number 6. So C4 comes out to be equation number 8. Is it clear to everyone what we are doing? Hello?
Yes, sir.
Once we know C3, C4, then we can put this C3, C4 in equation number 5 and we can calculate C2. So we have calculated again C2. Once we know C2, C4, C3, all these three things you can put back in these two equations, C2, C3, C4, and you can find out what is the distribution of temperature Tm and what is the distribution of temperature Tc. So with that, we have obtained this equation Tm and Tc. Is it clear to everyone?
Yes, sir.
So these are the expressions slightly different compared to the expressions which we have obtained earlier. Okay, and these are more realistic expressions. All right, is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
Okay. So please stop me if something is not clear. I will not mind it to explain it several times. If you ask me 10 times, I will be happy to explain even 100 times. Okay. So if something is not clear, please say so in between. Okay. All right. So this is all about the heat transfer coefficient. So these slides also I have uploaded on Teams. Okay. So let's move to the next topic. Next topic is a forced convection. Okay. So let me share the another slides. So far everything is clear to everybody what we are saying?
Yes, sir.
So why very few people are attending the classes? What happened? They feel that this subject is very easy. Is that the reason, or they don't attend any of the classes? Which one is true? I have seen that initial classes almost we used to have around 100. Now it is 50. And God knows by the end of this course, maybe 10 or maximum 10-20 people will be attending. That's what I have seen even in the tutorial. Maximum 20 people are attending. So what is the problem? Anybody? So is it not? I'm just trying to understand. Do you want me to improve in some way so that people will attend? Okay. If something is not clear, if I'm not good, or please tell me clearly. If you need something to be improved, please tell me clearly. Okay.
नहीं सर सब सही है सर.
I don't mind doing even better than this. Okay.
No sir, it's good. I think some of the people they are not wake up in morning. That's why I think.
Wake up in the morning. I mean, okay. No, why I am saying is because see, when people don't attend, then I don't know what is happening these days, but in my time, I used to attend. In fact, in my BTech, I have attended all the classes, no matter whether the class is good, bad, worst, doesn't matter. But I have attended all the classes. I don't remember missing even a single class. Okay. But these days, even everything is online. You can attend it from your own place of comfort. Still, people are not attending. See, everything then reflects in your performance later. Okay, this is what the seriousness. See, if you don't attend the classes, that seriousness will not come, isn't it? And that seriousness will not come, then eventually you will find the course boring. Eventually you will find the course not at all, worth looking at. And that's why I insist people to attend the class, because if you attend the class, then at least some delta X new thing you will get to know, isn't it? All right, let's not drag this discussion too much. I'm sorry to ask this, but I request everyone to attend if they look at this offline recording. Please attend the classes. Okay. And if you need anything to be changed, anything to be made more informative, or any change you want me to do, please feel free to tell me. Okay. Anyway. So is the slides visible to everyone?
Yes, sir.
Okay. Let me. Okay. So now let's look at forced convection. So far we have looked at conduction. In the conduction also we started with a very simple, one directional heat conduction. We have started with no modifications initially, a simple, you can see a flat slab we have taken initially. Then we eventually added some difficulties. We started looking at the curved surfaces like cylinder or sphere. Then we added the heat generation source. Then we have added the accumulation term. Then we have added the multi-dimensional conduction. After that, we have started looking at heat conduction and convection together, isn't it? Heat conduction and convection together we have looked at, isn't it? So you can see that slowly we are trying to add more and more difficulties in our analysis. Do you all agree? Yes or no?
Yes, sir.
So now let's look at the forced convection. So as I said in the previous slides that convection, there are two types: natural convection and the forced convection. In a natural convection, what happens is the turbulence in the fluid is generated only because of the density difference, and no external mean is used for creating the turbulence. But in a forced convection, you use the external mechanical unit in order to create the turbulence. Okay. So forced convection is always with some mechanical unit you add the turbulence in the fluid. All right. Now another important thing, remember I said that it's not difficult to write the balance equation in a heat transfer. Whatever the system you might be having, if there is a change in area, if there are accumulation term is there, or even if there is a generation term is there, multi-dimensional is there, in any case you can assume a element, isn't it, in the system, and then you can do the balance of all the input output accumulation and the generation terms and get the partial differential equations, isn't it? So that's not difficult. You can make the elemental balance here and get the partial differential equations. But the problem comes in what? Problem comes is, even though you get the balance equations in terms of partial differential equations, you will not be able to solve them because these are going to become too complex to solve. So in a practical cases, it becomes formidable task to solve such equations for calculation of the heat transfer rates. It's not about whether we can make the balance or not, isn't it? You can derive the Navier-Stokes equation from the first principle, isn't it? So that's the easy part. Difficult part is, can you solve the Navier-Stokes equation accurately? You got the point what I'm trying to say?
Yes, sir.
Isn't it? So it's not that the balance equation you cannot make. You can make the balance equation for any system. There is no problem in that. The problem comes in whether you will be able to solve it or not. You will not be able to solve it. Okay. Another thing is, so in order to eliminate this difficulty, what we have assumed in the last slide, previous slides, in the heat transfer coefficient, we said that we will not solve this differential equation. Let's make our life easier. So instead of, so see, all these differential equations are coming from what? They are coming from the primarily because of flow, isn't it? So, and based on this flow, finally you are calculating the heat transfer coefficient, and that heat transfer coefficient is going to give you the total heat transfer, isn't it? So now the question is, if I calculate this heat transfer coefficient directly using some empirical correlations, using some data, then I don't need to solve all these complex, model equation, isn't it? That's what the rationale behind what we have discussed in the previous class, isn't it? That was the rationale behind the this constant rationale behind this particular variable which is called as heat transfer coefficient, isn't it? We have formulated the concept of heat transfer coefficient primarily because we don't want to solve the complex mathematical equation. Instead of that, we can use the available data. From that data, we will make some correlations, and with those correlations, we can calculate the heat transfer coefficient directly, and that heat transfer coefficient we are going to use in the heat transfer calculation instead of solving the model equations from the first principle. So of course, as I said that in this case, the heat transfer correlations we are going to use. That means what? These correlations will not be very accurate. So very often they have the error up to 25 to 30%. But that's okay. At least it enables you to solve the problem. Do you all agree or not? Isn't it?
Yes, sir.
So,
Please go ahead.
when we say that solution of Navier-Stokes equation is not possible, we mean analytical solution, or is it not possible to solve it numerically also?
Even numerical solution also you make some assumptions. So you either assume inviscid flow or you assume that whether there is a Stokes flow or inviscid flow, all those assumptions you make, and based on that some of the terms of the Navier-Stokes equation you eliminate and then you solve numerically. Got the point? You don't solve it completely. Even solving a complete Navier-Stokes equation numerically is also going to be very difficult. Very difficult. Do you agree or not agree? All these CFD people, they don't solve the Navier-Stokes equation exactly. They first see whether their system is a viscous system or a non-viscous system. Based on that, some of the terms become zero. And then you solve only the simplified form of the Navier-Stokes equation, that too using numerical methods. That is what the basis of entire CFD is. Correct?
Yes, sir.
Okay. Yes or no?
So
what point I'm trying to make is even with the fastest computer you are having, it will be a really difficult task to solve the complete Navier-Stokes equation, because it's going to take huge computational effort, isn't it? Because see, in the complete Navier-Stokes equation, you have a flow in all three directions, and there is another direction which is time. Do you able to recall it? Remember the generalized Navier-Stokes equation, which is given in terms of substantial derivative, isn't it? Capital D.
Yes.
Isn't it? That has all four terms: time, X, Y, and Z.
Yes, sir.
Isn't it? So very often it becomes very difficult to solve. And again, on the right hand side, so see, left hand side is the accumulation term, but right hand side you have a pressure term, then you have viscous dissipation term, and then again you have a gravitational force, etc. Isn't it? So all three are there. So depending on what type of system you are using, some of these terms become zero, and then you solve it. Does it make sense what I'm saying?
Yes, sir.
Yes, sir.
Okay. So point what we are making here is, even if we solve the Navier-Stokes equation, that is going to give us the velocity. Okay. That is going to give us the velocity profile. And then also, in addition to that, some other parameters are also important, like the change in the viscosity, change in the density, all those changes one need to incorporate while calculating the heat transfer coefficient, isn't it? Heat transfer coefficient not only depends on the velocity, but it also depends on what? It also depends on specific heat. It also depends on density. It also depends on viscosity, isn't it? And these are going to change with temperature, isn't it? When there is a flow occurring, then there is a temperature changing across the pipe, isn't it? And that means what? The properties of this the fluid at different location will be different, isn't it? So all these has to be accounted in order to solve the complete problem mathematically, and it becomes really difficult to solve, isn't it? Do you agree or not?
Yes, sir.
And therefore all these complexities are accounted only in the heat transfer coefficient, and we are saying that this heat transfer coefficient, instead of calculating this analytically we will calculate it using some data available on the systems, using some empirical correlations. Of course, that will have almost 25 to 30% error, but it's okay. You are at least getting some solution. But if you try to formulate the mathematical problem here, you might not get even the solution at all. Isn't it?
Yes, sir.
Okay. Okay, so let's look at some of the difficulties. Now the difficulty is, see, okay, although the simplest way to visualize convective heat transfer to or from a surface is to assume the existence of stagnant film at the wall, okay, and no such film exists in reality. So remember, when we have started looking at the definition of heat transfer coefficient, we have obtained the heat transfer coefficient as K by delta, if you remember, isn't it? Correct? Yes. K by delta, that's what we have obtained, where K is the thermal conductivity of the fluid and delta will be the film thickness. So film thickness is the thickness of the film which is very close to the surface of the solid. And what we are assuming there that this film essentially remains stagnant even though the fluid is moving, but doesn't matter whether the flow is laminar or turbulent, a small film near to the surface of the solid will always remain at, almost near to zero velocity, almost remain stagnant. But is it completely stagnant? Is it completely stagnant? Do you think it will be just, there will not be any movement of the fluid elements there? It's not like that. There will be some movement of the fluid. It's a fluid, isn't it? It's not a solid. You will have some fluid particle elements, but that movement is very small and therefore we are assuming that it's stagnant, but it's not actually stagnant. That's what it means, isn't it? Do you all agree?
Yes, sir.
So that's what we are saying. No such film does exist in reality. Okay. It is true, however, that in case of heat transfer from the surface, most of the heat transfer resistance is offered by this narrow zone of fluid near the surface called the boundary layer, but the fluid in this zone is never stagnant. Okay. So that's what, see, while calculating the heat transfer coefficient, we have assumed that the complete temperature drop is taking place in this narrow film. That's what we have assumed for calculating the heat transfer coefficient, isn't it? So when we are assuming that this film is stagnant and all the resistances offered in this small film itself, then and then only you can apply this Fourier's law of heat conduction there and you can calculate H equals to K by delta. Yes or no? Correct. Does it make sense or not? Hello? Not clear? Please say so. If something is not clear, please say so. Not clear? Hello? What happened? Am I audible?
Yes, sir, you are audible.
So is it clear or not clear? Maybe I will open again. Just a minute. Okay. So that confidence is lacking in your, assurance. So it indicates me that it's not clear. Okay. Let me just open the previous slides which we have looked at. Okay. Maybe that will put some more light on what we are discussing. Okay. So this is what we have seen in the heat transfer coefficient, isn't it? This is what the slide which we have looked at earlier, right? So see, this is the bulk flow occurring here, and what we are assuming that a very small film which is close to this surface, the maximum temperature difference is most of the temperature difference is occurring in this film. But it's not that the total temperature difference is occurring only in this film. There is some more temperature difference occurring over this entire length here, isn't it?
Yes, sir.
Also, we are assuming that this particular film is completely stagnant, but it's not. It's not. It is not going to be completely stagnant. Some fluid element, movement of the fluid element is going to be there in this particular film because this bulk is flowing. Of course, the first layer, which is very close to this hot surface, will be at zero velocity because of no slip condition, but all the subsequent layers in this film will have some velocity. Do you all agree or not?
Yes, sir.
So that means this assumption that this film is completely stagnant is only an assumption. It's not, completely true. And also this temperature difference, the complete temperature difference is occurring only in the film. That is also an assumption, isn't it? Some variation will still occur in the bulk. Okay, so that's what we are trying to say here.
So
Please go ahead.
if the film flows along the plate, then what is the difference if it's stagnant
So
or
plate
it's
is
not?
not moving.
No,
Basically, we are saying plate is moving, fluid is moving, and plate is stagnant. So this is something like pipe is there. Pipe remains at the same place, isn't it? But the fluid inside the pipe is moving, isn't it? So the fluid elements which are very close to the surface of the pipe will be at the zero velocity.
yes, sir.
That's what we are assuming. Only thing is that instead of a pipe, we are using a flat plate here.
But then the temperature would be the same function of the height from plate now. I mean, if the film is stagnant, then also the temperature is function of that height from plate, and if the fluid is moving parallel to the plate, then
Yes. You are absolutely correct in that. But whether we will be able to apply the Fourier's law of heat conduction there? Remember this entire equation which we have obtained based on the Fourier's law of heat conduction, and the Fourier's law of heat conduction is applicable only if the film is stagnant.
yes, sir.
Isn't it? So what I'm trying to say here is there are several things which we will not be able to account accurately. So rationale behind putting this particular slide is primarily to appreciate the fact that we will not be able to make the accurate modeling. There will be several things which we will not be able to account, and therefore the concept of heat transfer coefficient is is still important, because all these uncertain things we can couple directly in the heat transfer coefficient. Does it make sense?
Yes, sir.
Also, the concept of boundary layer is going to be very important here, because the flow, understanding the flow and the heat transfer characteristic near the wall is going to play an important role in deciding what will be the value of heat transfer coefficient, isn't it? Okay, now let's look at the example here. So there is a flat plate. This is the flat plate. Okay, at some temperature maybe. Okay, again the fluid is flowing across this flat plate. Okay, so you can see that the fluid layer which is very close to this surface will have a zero velocity, but as we move up, you can see that the fluid velocity is going to increase, and at this red line it is going to become the free stream velocity. Yes or no? Correct?
Yes.
Hello?
No, sir, I did not
Yes,
understand.
sir.
So see, velocity of the fluid is V, isn't it? Let's say we are having the velocity which is uniform across this Y direction. Okay, V is there completely. Okay.
Yes, sir.
So, but when this fluid which is moving with this uniform velocity passes across this flat surface, what will happen to the velocity here at the boundary of the boundary between the fluid and the solid surface? What will be the fluid velocity here?
So 0, no slip boundary condition.
No slip boundary. But as you move up in a y direction, let's say, what will happen to the velocity of the fluid in this boundary layer? This is the boundary layer, isn't it?
So the magnitude would be less than v, but there would be some velocity.
Some velocity. And eventually, when you reach to this boundary layer here, remember this is the red line, shows the boundary layer. So when you reach to this red line, then the velocity becomes same as this v, isn't it? Free stream velocity.
Yes, sir.
That's what I have plotted here, isn't it? But this thickness of the boundary layer is going to vary, isn't it? So initially, as your length x, as your distance from the leading edge here, x is increasing. Initially, up to this, you will have a laminar boundary layer. Then you will have a small region, you will have like this, which will have a transition zone, and then you will have a turbulent boundary layer where you will have some eddies, buffer zone, etc. Do you all agree or not? This is what the concept of boundary layer is, isn't it? If a fluid is passed over a plate like this, isn't it? This is how the boundary layer going to form. Yes or no?
So it's not an infinite plate, right?
It's not an infinite plate. Some length is there. That's what we are not looking at so far. Why that question is infinite plate?
No, I mean it's just there wouldn't be boundary in that case, no boundary layer. They would be just laminar, I believe.
No. So what the only point here is, after this point, we will have a turbulent boundary layer. So even though this plate is infinite, we will have a turbulent boundary layer. Isn't it? This will be a turbulent boundary layer after this.
But there are developing and developed regions, that kind of regions are there.
That will be there, but in this case, what we are only looking at is, we are looking at up to what length we will have a laminar boundary layer, up to what length we will have a transition boundary layer, and beyond that we will have a turbulent boundary layer. That's what we are trying to say. Okay.
Yes, sir.
Okay. So is it clear or not clear? This you might have seen in fluid mechanics. So have you done your fluid mechanics so far? No.
Yeah, so only transport phenomena.
Transport phenomena. Okay. So you will get to know more about the boundary layer when you will look at fluid mechanics. Okay. So this is something called as a boundary layer, and common example is, how many of you have taken a bath in the river? All of you?
Yes, sir.
No, sir.
So okay, so I don't know whether you remember or not, but if not, then next time when you go, just put your hand inside the water and see what type of shape it makes. You will see that some type of boundary layer, it will be above your hand. Similar type of profile you will form there. Okay.
Yes, sir.
I don't know whether you have done this or not, but if not, then do this. Okay, just see what type of shape of the flow you get there. All right. Okay. So point to note down here in this slide is, as our distance from this leading edge increases, initially I have a laminar boundary layer. So when I'm saying a laminar boundary layer, what it means is the fluid layers are moving in a orderly manner. That is what the laminar flow is, isn't it? But beyond this particular point here, then there is a turbulence starts adding in, and that up to this we call it as a transition zone, and after the transition zone there is a turbulent boundary layer where you will have eddies, wake formation, many other things will be there. Is it clear to everyone?
Yes, sir.
Now for a flow passed over a flat plate, the critical laminar critical Reynolds number here is, 5 into 10 raised to the power 5. So if my Reynolds number is less than equals to 5 into 10 raised to power 5, then I have a laminar boundary layer, and how the Reynolds number is calculated? Reynolds number is calculated based on the distance from the leading edge. That's why it is defined as REX. Okay, Reynolds number calculated in terms of this distance x from this leading edge here. Okay, so it is given as rho v x by mu, where rho is the density of the fluid, v is the velocity of the fluid, v is this free stream velocity. Okay, not the velocity here. So here v is the free stream velocity. So rho v x divided by mu. So that's how you calculate the Reynolds number. And if this Reynolds number REX is less than equals to 5 into 10 raised to power 5, then my flow is laminar. And between 5 into 10 raised to power 5 and 10 raised to 6, it's a transition zone. And if it is greater than 10 raised to power 6, then it's a turbulent zone. So similar problem we have solved in the tutorial yesterday, isn't it? So there we have used only laminar and turbulent zone. We have also assumed that this transition zone is a part of turbulent zone itself, isn't it? That was the difference which we have done in the last tutorial class, if you remember. Okay, is it clear to everyone?
Yes, sir.
Because no equation was given for the transition zone there. So we have assumed that the transition zone also accounted through this equation of turbulent zone. That's what we have, assumed there. So this is only for a flat plate. This critical Reynolds number here is only for a flat plate. But if you use a pipe flow, for a pipe flow, critical Reynolds number is what? Anyone?
So 21.
2100, correct. So similarly, if you look at some other geometry, flow path across the cylinder, then you will have some different critical Reynolds number. Okay, this Reynolds number is only for a flow passed over a flat plate. Is it clear?
Yes, sir.
Okay, now please go ahead.
This expression of Reynolds number, is it derived or experimentally observed?
Reynolds number is okay. What is Reynolds number?
For pipe, it was rho.
How it is defined? Reynolds number is inertia force divided by viscous force, if you remember, isn't it? Yes or no? Do you remember or not remember?
Yes, sir.
Achha. So Reynolds number is okay. So why we are taking this Reynolds number, etc. Because you will see that when we are looking at the flow behavior or the heat transfer or even the mass transfer, these are governed by several dimensionless groups. For instance, flow is mostly governed by Reynolds number, but if you look at the heat transfer is mostly governed by several dimensionless group like Reynolds number, Nusselt number, also Prandtl number, etc. There is some physical significance behind them. Physical significance behind them is, for instance, Reynolds number, when we are saying it is the ratio of inertia force to viscous force. So which force is more dominating, that you can calculate based on the Reynolds number. Okay. Is it clear? Yes or no?
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
So that is why several of these dimensionless groups are, formulated. Sorry. Okay, we will see all these little bit in more detail as we move to the subsequent slides. There you will appreciate little bit more. Okay. So in fact, that's what we are going to look at, how these dimensionless groups are used, what is the rationale behind using them, and what is the basis of using these dimensionless groups for quantifying the heat transfer or a flow behavior. Okay, that we will see. Okay. Now the next concept is, okay, so far we have looked at, this is the momentum boundary layer, isn't it? Momentum boundary layer or a velocity boundary layer. Okay, so velocity profile here, you can see that between this boundary layer and this surface, you will have some velocity profile as shown here. Can you see? Yes or no?
Yes, sir.
So here velocity is 0. Here you will have a free stream velocity, and in between you have a distribution of the velocity. And this velocity profile you can obtain by solving the boundary layer problem. And it depends on what is the length of what is the distance from the leading edge. So for instance, this is the leading edge. So what is the distance of the location from the leading edge? That is nothing but x. It depends on the x. You can see that the boundary layer thickness and the velocity profile is a function of x. Okay, is it clear? Hello?
Yes, sir.
Okay, all right. So now similar to this, please go ahead. Is there any question? Hello? Is there any question? Please unmute if there is no question. Hello? Okay, sorry, thank you. Okay. Is the slides visible to everyone?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So now similar to the velocity boundary layer or a momentum boundary layer, there exists a thermal boundary layer. So thermal boundary layer is what? For instance, if I am having a free stream like this, which having the velocity V and temperature T naught, and the temperature of this surface, temperature of this plate is Ts, how my temperature profile will look like? Temperature profile will also look like similar to this. How my temperature is going to change. Difference in the temperature will look like, isn't it? So here the temperature, actual temperature minus the temperature of the plate will be 0 here, but as you move here, you will get the temperature difference will be as what? You will have a temperature difference will be Ts minus T. Ts minus T naught. Correct? And similar to the momentum boundary layer, you will also get a thermal boundary layer. Can you see the point?
Yes, sir.
So not only the thermal boundary layer, you can also get a boundary layer in terms of concentration. If you are, trying to understand this problem in the perspective of mass transfer, you can get even a concentration boundary layer similar to this, isn't it? So I am just trying to connect it with your transport phenomena, isn't it? So momentum boundary layer basically looks into the flow. Thermal boundary layer is primarily looking into the heat, whereas the concentration boundary layer you will get in terms of the mass transfer. Do you all agree or not?
Yes, sir.
Okay. Now, the interesting point to note down here is this thermal boundary layer, which we have shown by a red line, and the velocity boundary layer we have shown by a blue line. It need not be the same. They can be different. They can be different. It depends on the Prandtl number. It depends on the Prandtl number. So Prandtl number is nothing but kinematic viscosity divided by the momentum diffusivity. Remember, kinematic viscosity and the diffusivity both have the same units, isn't it? So if we divide kinematic viscosity, which is nothing but what? Mu by rho divided by K by rho Cp, that is nothing but the thermal diffusivity. So if we do that, what we are going to get? Cp mu by K, that's what we are going to get. So Prandtl number is defined as Cp mu by K. Okay, so momentum boundary layer and the thermal boundary layer both are going to coincide with each other when the Prandtl number is equals to 1. But when Prandtl number is less than 1, then this momentum boundary layer will be within the thermal boundary layer. Whereas when Prandtl number is greater than 1, then thermal boundary layer will be within the momentum boundary layer. So this concept of boundary layer is very important because it is going to, remember that what we are assuming that within this boundary layer there is a velocity distribution is there. Beyond that there is a free stream velocity, correct? Or free stream temperature, isn't it? So that means most of the resistance to the heat transfer or a flow are occurring primarily in what? Boundary layer. Do you all agree or not?
Yes, sir.
That's
Yes.
why we are looking at this concept of boundary layer. And again, this thickness of this boundary layer is changing with the distance from the leading edge. Correct. So that means what? The velocity distribution or a temperature distribution in the boundary layer is going to vary as you move from this leading edge. That means what? The heat transfer coefficient which you are going to calculate as you are moving from this leading edge is going to vary as your distance from the leading edge is varying. Do you all agree or not?
Yes, sir.
Isn't it? But very often the heat transfer correlations are given in terms of the average heat transfer coefficient. But in this case, you can see that the heat transfer coefficient is varying as you are moving from the leading edge. Yes or no? So that means all these variation effects has to be accounted in the average heat transfer coefficient. Then and then only it is going to make sense. Does it make sense to everyone what I'm trying to say? Remember, heat transfer coefficient here will be different, here it will be different because it depends on the velocity profile or this boundary layer of temperature boundary layer, isn't it? And the temperature boundary layer thickness is changing. That means its temperature profile is going to vary. Similarly, the velocity profile is going to vary. That means heat transfer coefficient is going to vary as you move along this plate. But in a real life, problem solving, very often you use the correlations which define the heat transfer coefficient in terms of average heat transfer coefficient. So all these variation effects has to be accounted directly there. Yes or no?
Yes.
Yes.
So this is what we have looked at, the one of the problem which we have solved in the last tutorial, where we have finally calculated the average heat transfer coefficient, isn't it? Initially we have calculated the local heat transfer coefficient for laminar and turbulent region, and finally using this entire thing we have calculated the average heat transfer coefficient. That's what we have done in the last tutorial, if you have attended. Does it make sense now, everything?
Yes, sir.
Yes, sir.
Okay, let us take another example. Let us take another example to appreciate the concept. Okay, so let's say we are having a spherical, let's say we are having a cylinder like this. Okay, we are having a cylindrical pipe is there, and in the cylindrical pipe some hot fluid is flowing and we wanted to cool that fluid. So what we are doing, we are blowing the air with a constant velocity and temperature T0 across this cylinder. So can you see that the cylinder is moving in a Z direction? Okay, whereas the fluid is moving across the cylinder like this, isn't it? Can you
visualize
the actual system?
Yes, sir.
Now, in this case, you can see that when this fluid reaches to this boundary here, exactly at this tip here, stagnation point. So this is the point at which the velocity becomes 0, isn't it? This is the stagnation point. Do you all agree? Yes or no? Because this cylinder is fixed, it's not moving. Cylinder, this air is moving, so the air you have blown over this cylinder, across the cylinder. So at this point, at this center point here, the velocity of the fluid will be 0. Do you agree with me? Yes or no? Again, how the boundary layer will be going to develop in this case? You will have a boundary layer which is shown by a green, a blue line here, isn't it? That's how the boundary layer will be developed here. And if you look at the velocity profile, a typical velocity profile here, you can see that at this sphere, at the cylindrical surface here, the velocity will be 0, but as you move away from the cylindrical surface, there will be some velocity and it will eventually reach to this, isn't it? Yes or no?
Yes, sir.
Correct. But the interesting point to note that this velocity profile is, you know, so see, your velocity profile is just, you can see this, the velocity is 0 here, and it is then increasing all the way to the free stream velocity till this point here. But as you move further here, you can see that your velocity here is 0, but then at this point your backward flow starts generating in, and eventually your velocity profile becomes like this, where there is a backflow is occurring. So you will have a reverse velocity profile here, and then a positive velocity profile in the remaining part. Do you all agree or not?
Sir, why backward flow?
Because see, remember here this flow separation is going to occur around this point, isn't it? And then what will happen is there will be eddies formation will be there here, isn't it? And that will provide that will give you a backflow here, isn't it? Because here also see, at this point there is no flow here, isn't it? Remember, this fluid will move like this, but there will be a backflow here in this direction. Yes, no? Yes or no?
Yes, sir.
Yes, sir.
So that backward flow is going to give you a backward velocity like this, and then there will be a positive velocity here for the remaining part. Now, with this all these complications here, you can see that as your theta increases, your velocity profile is varying. So if you look at the heat transfer coefficient, your heat transfer coefficient will also vary across this length, isn't it? It's not going to be heat transfer coefficient here will be something else. Here you will have some different heat transfer coefficient, isn't it? So are you going to calculate the heat transfer coefficient based on some such local points, or you need to have a heat transfer coefficient which describes this entire system together? Definitely you wanted to make your life easy, isn't it? So you definitely try to develop the heat transfer coefficient, which is the average value accounting all these variations. Do you agree with me or not?
Yes, sir.
Isn't it? Otherwise, if I write down the heat transfer coefficient only for this point, then I will not be able to solve this other, isn't it? That heat transfer coefficient will be applicable only at this point or this point, isn't it? So it's not going to serve my purpose if I find out the heat transfer coefficient correlation for a local values, isn't it? Do you agree or not?
Yes, sir.
Yes.
Isn't it? So again, here you can see. So see, here what happens is initially my heat transfer coefficient is going to decrease. My heat transfer coefficient is going to decrease as you move from this up to almost 90 degrees Celsius. Why? It's not a fixed boundary. It's not fixed boundary. It will be slightly more than 90. Okay. Why? Because as you move from this 0 degree to up to 90 degree, you can see that your thickness of your boundary layer increasing, isn't it? Thickness of your boundary layer is increasing here. And how the H is given? K by delta? Yes or no?
Yes, sir.
So here delta is increasing. So what will be the heat transfer coefficient? H. K is fixed, isn't it? K is the thermal conductivity of the fluid. Divided by delta is the thickness of the boundary layer. We are assuming that the boundary layer is remaining stagnant, isn't it? Even though it's not a stagnant, isn't it? It's not a stagnant. Some velocity profile is there, but for a transfer calculation, we are assuming that the boundary layer is stagnant. Let's say, so K by delta. So delta is increasing. That means what? H will be decreasing. So that's why we are going from 0 degree here to 90 degree here up to this. You can see that your K by delta is decreasing, so heat transfer coefficient is decreasing, and Nusselt number is what? HD by K, isn't it? So Nusselt number is also decreasing, or H, we can write this, even if I plot this graph in terms of H, I will get a same nature, isn't it? So my heat transfer coefficient start decreasing up to almost this point, which is the separation point. After the separation point, you can see that the heat transfer coefficient start increasing. Why it's so?
Sir, the reverse flow.
because of this reverse flow, there is a turbulence added. And because of additional turbulence, there is a more heat transfer coefficient now. Isn't it? You are adding more turbulence here, and because of your heat transfer coefficient increases. So that means you can see that the heat transfer coefficient for decreases and then increases, and this entire thing has to be correlated in an average heat transfer coefficient. That's why this concept of average heat transfer coefficient is used instead of taking the local heat transfer coefficient. Does it make sense to everyone? Hello?
Yes, sir.
Okay. All right. Now, as one of our friends said, what these dimensionless groups are. Okay. So we are going to do a dimensionless analysis, dimensional analysis. Dimensional analysis is used in order to decide what are the different dimensionless groups which are going to quantify the flow or heat transfer. Okay. In a given system. So, okay, so I will just look at this slide and then we will conclude today's class. More details on this we will look at in the subsequent class. So, okay, let's read through. Though solving the heat transfer problem became possible due to high-speed computers, the way to solve these easily for approximate results is the use of correlation in terms of dimensionless groups. So that's what we said, isn't it? With the higher computational computational resources available these days, you can solve the problem, but it is going to take long time. But you can get the approximate results directly using the correlations in terms of dimensionless groups. So the technique of dimensional analysis is a powerful tool to identify the dimensionless groups which are used to correlate the variables that influence a particular physical process. For instance, in a heat transfer coefficient, if you wanted to look at how the heat transfer coefficient is going to vary, we might need to find out what are the different dimensionless groups which will be required to correlate the heat transfer coefficient. In fact, you will see that all these empirical correlations used in the heat transfer, these are with respect to some dimensionless group. Okay. So which dimensionless group should be used in the particular correlation, that depends on that you can find out using dimensional analysis. Okay. So the first step is to identify the relevant variables, parameters or properties. For example, in case of a convective heat transfer to a fluid flowing through a circular pipe. So if there is a flow is taking place through a circular pipe, from our experimental finding and our understanding of the physical phenomena, what we can say that the heat transfer coefficient H depends upon the fluid velocity. It depends on the diameter of the pipe. It depends on the thermal conductivity of the fluid. It depends on the specific heat of the fluid, density of the fluid and viscosity. So H, V, D, K, Cp, rho, mu are the variables which are need to be looked at when we are looking at heat transfer through the circular pipe. Okay, and the dimensionless groups will be formed based on these variables. Okay, so dimensional analysis teaches us how to cluster two or more of these quantities. Again, there is an interesting theorem which is called as a Buckingham Pi theorem. I don't know whether you will get to know about this in your fluid mechanics or not, but what this theorem states that if the equation, let's say phi, in terms of let's say different variables x1, x2, xn equals to 0 is the only relation among the quantities x1, x2, xn, and if it holds for any arbitrary choice of the units in which these quantities are measured, then the solution of this equation has the form f of pi 1, pi 2, pi m equals to 0, where pi 1, pi 2, pi m, these are the independent dimensionless groups, which are in terms of x's, where x's are nothing but what? Variables. Further, P is the number of primary quantities necessary to express the dimensions of x's. So P is the primary quantity. So there are only 7 primary quantities. Remember, mass, length, then temperature, time, luminous intensity, current, and the moles, isn't it? These are only the 7 primary quantities are there. So all these excess will be represented in terms of primary quantities, and then these are grouped in terms of the dimensionless groups. Okay, so usually this relation is there, n minus m equals to p, where n is the number of variables, m is the number of dimensionless groups, and their subtraction should be equals to number of primary quantities. Okay, so for instance, if you are looking at the convective heat transfer between for the flow through the circular pipe, in this case, how many variables we are having? 1, 2, 3, 4, 5, 6, 7 variables are there. H, V, D, K, Cp, rho, and mu. So these 7 variables, so n will be 7, isn't it? How many primary quantities required in this case? You will, if you look at the dimensions of all these, you will see that only 4 primary quantities are used here: mass, length, time, and temperature. Isn't it? So only 4 primary quantities are used here. So n 7 minus this p if I use, which is nothing but 4. So 7 minus 3, 7 minus 4 will be what? 3. So in this case, 3 dimensionless groups we are expected to get. So my heat transfer coefficient, which I am interested in, my heat transfer coefficient will be correlated in terms of 3 dimensionless groups. Is it clear to everyone?
Yes, sir.
Yes.
So have you studied this Buckingham pi theorem before? Any of you?
Sir.
Yes or no?
No, sir.
No, sir.
In your JEE days? No?
No, sir.
No, sir.
Not at all. Okay, sorry. So we will continue from this point in the next class. Is there any question so far? Hello?
Sir, I had a doubt regarding
Please.
the no slip boundary condition.
Please go ahead.
Sir, why do we know that there is a no slip boundary? How do we know it?
Acha, so what we are, okay. Okay, so look at the practical, application. Okay, so if you, let's say, if you take your palm, okay, if you take your palm and let's say you put a water on that, okay, you put a water on that. Do you think instantaneously you can take all the water molecules from your palm? Can you take it? Unless you keep your hand in a sun and let it evaporate. But can you take all the water away from your palm?
No, sir.
Why?
That's because of the, I don't know what, cohesion, adhesion forces.
So that means the fluid particles which are in contact with your palm, isn't it? That will be sticking there, isn't it? They will not be moving. Yes or no?
Yes, sir, but that also depends upon the material. Like my palm has got more of the attractive forces.
All right. So you are absolutely correct. So you are saying that if I use, instead of water, if I use a mercury, in that case it is not going to stick. That's what you are saying?
Yes, sir. Yes, sir.
Completely agree. Completely agree. Isn't it? But this no slip condition, okay. So see, most of the time when we are using the flow through a pipe or flow through any system, the typical fluids we use is what? Typical fluid is used is water, isn't it? Which sticks to that. So some adhesion is there. Correct. Your point is correct. When there is a fluid which is having the fluid like mercury is there, which has the contact angle almost around 180 or something more than that, isn't it? So that means it's not going to stick to your surface. But when you are okay, so how often you flow the mercury there, isn't it? And it depends on the surface also, isn't it? Isn't it? So see,
Yes.
the contact angle depends on both metal surface as well as the fluid, isn't it?
Fluid. Yes, sir.
Correct. So very often you will see that most of the time you will see that there is some adhesive force will be there, isn't it? Correct. Yes or no?
Yes, sir.
So because of that, the fluid which is very close to the surface, that is not going to move and that will have a zero velocity. That is what in general the basis of this no slip condition is. Does it make sense?
Yes, sir. Sir, but then there is a question ki, till how many layers of that fluid will not move?
Okay, so that anyway we are accounting in terms of velocity profile.
Yes, sir.
Isn't it? That's what the point. That's why you get the velocity profile. You don't get the rod-like velocity profile in the pipe flow. You get a parabolic profile like this, isn't it? It's because the fluid elements, one layer is offering resistance on other.
Yes, sir. Sir, but I'm not able to get, like, there is a our surface, then there is a boundary layer, which contains only the first molecules of water which are sticking to the surface. And then there is again a layer of water, but for that another layer, there is a boundary condition.
Okay, just that is what the another layer will offer the resistance by the virtue of viscosity.
Yes, sir.
Okay, so that is what viscosity, definition of viscosity is, isn't it? The resistance offered by one fluid layer over the other is nothing but the viscosity.
Yes, sir. Okay.
Okay, so it's not going to slide without any resistance. There will be some viscosity, viscous resistance will be there.
Okay, sir. Yes.
Is it clear? Is there any question? Any more question?
No, sir.
Okay, guys, then see you all when?
Monday.
Monday. Okay. Yes. So see you all on Monday.